Good evening, friends. This lecture of electromagnetic radiation in clinical oncology is a very elementary lecture. So far as radiation oncology is concerned, is entirely focused to the resident level, or particularly those residents who are just joined, the first year and second year residents. Then we should know basically which beam you are working and what are the energy, how we measure, and actually what is the basic knowledge about that, and radiation interaction with the matter, including this chapter. So myself, Major Dr. M. Q. Beg, radiation oncologist, JK Cancer Institute, presenting you the electromagnetic radiation in clinical oncology. The radiation is a form of energy can be emitted and propagated through the space of medium by different modes of energy transfer and deposition. The radiotherapy is basically used in a malignant disease that have also some partially to the non-malignant disease with the help of ionizing radiation. The radiation effect is usually produced by energy absorbed in the living tissue through the process of two processes. One is ionization, another is excitation. Both happen simultaneously at the atom and a molecule level. The radiation dose is the amount of energy absorbed by the tissue given, and a given dose need with an accuracy of plus minus 5%, although the current criteria is further refined is to up to 3 plus minus 3%. So that you must remember. There are 5 heads based on the radiation physics. First, how we produce the radiation. What are the methods of producing a radiation? I mean, it is a radioactive element or a electric, DC current, direct DC current. And the second part is the technology of a tumor localization, that is entirely encompassing the imaging in the tumor imaging. And the third part, once you have done a tumor imaging, beautiful imaging, and then you go towards the step of a radiation therapy planning of irradiation of a tissue which is intended to be irradiated. And third is the implementation of a treatment. These all include a chain of a team, which include the clinical oncologist, radiation oncologist, physicist, radiation technologist, as well as if you have radiation, if you are a radio diagnosis fellow, this is nothing less, this is very, very important. An estimation of a dose received by the different sites in the body. This which will covered, and you see here visible light, invisible light. You see the visible light, the high energy lights are non-visible basically, the gamma rays, X-rays, ultraviolet rays, it is basically not visible. And then a visible portion of light is very small, and then after that you go infrared, microwaves and radio waves, they are low energy radiations. These are all electromagnetic waves. So what are the types of radiation? That's one of the electromagnetic radiation. Second is the particulate radiation, electron, proton, alpha particle, these are the particulate radiation. X-rays, the gamma rays, radio wave, ultraviolet rays, infrared radiation, and electron, proton, alpha particle have gone in a particulate radiation. These are the types of radiations. So electromagnetic radiation, they are readily fluctuating electric and magnetic fields. When these electromagnetic waves travels, they have a two component, electric and magnetic field both. They travel with a light velocity, means 3 into 10 to the power 10 centimeter per second in a free space. These waves, both component, electric and magnetic component, they oscillate at the right angle to each other, at any instance of given wave. So this type of wave usually also called transverse wave because of oscillation at the right angles to the direction of the travel waves. That is why also called transverse wave. You see here the electromagnetic spectrum spectrum means is not one energy. Basically it's a spectrum of energy which you have a low energy, high energy, all mixed together. So you see the low frequency waves usually non-ionizing, you see here, but in ionizing they have a more transverse ups and downs in it means electrical and magnetical field. High frequency, these ionizing radiation is basically utilized in the clinical oncology. So what are the features of a transverse wave? The wavelength is basically a distance between two successive corresponding point on the wave, and the frequency and number of wave produced per second is called frequency. These are basic basic physics we learn in the 10+2 level. The velocity travel per second by distance travel by per second by wave, and amplitude, the highest point on the wave, it's a amplitude. So velocity is equal to lambda, that is wavelength, and a frequency mu. So you see here the electrical field and the magnetic field, you both see they are in the transverse direction, and you see the amplitude here beautifully, the maximum rise on the peak on the upside or the downside, it's the amplitude, and direction of propagation you see this way, this this waves travels. So since all electromagnetic waves have the same velocity, the frequency of any such radiation is inversely proportional to its wavelength. An electromagnetic radiation carry energy in form of packet or bundle called photon or quantum. They travel with a light velocity. The energy of photon is usually equal to the universal constant, Planck constant, that is a medium, and frequency, or means shorter the wavelength, greater the frequency, and greater the photon energy. If a high photon energy you are using, that you deemed it's a high frequency and a low wavelength. So that we basically usually clinically see the gamma rays and X-rays. Both are similar properties, have just a change, no change mass. They have a nature of property, they don't know, they don't have literally no mass, but they are unaffected by magnetic field. The only difference between the X-rays and the gamma rays is basically the origin. The gamma ray is basically is simultaneously released with a beta particle. It's from the nucleus, like which happens in the cobalt. If somebody asks you what emits from the cobalt, do not tell about the only gamma rays release. The gamma rays as well as the beta particle both release. So an X-ray is basically produced by the orbital electron, and usually in a linear accelerator they produce the X-rays. So gamma rays produced by the nucleus of the atom while passing through the medium. Electromagnetic waves get attenuated. If electromagnetic waves they traverse by any medium, they get attenuated. And how they attenuated? Like incidental beam intensity, if I, then if a thickness of a medium is m, there is a fractional decrease in the intensity per unit thickness of a material, which is expressed in per centimeter. That is I is equal to I0 exponential upon mt. That indicates that the thickness of material as much as high, that the intensity of a beam will be reduced. So in radiology, electrical charge involve often that of electrons, so the energy expressed in the electron volt. Usually energy is expressed in the electron volt. What are the common properties shared by electromagnetic waves? They all travel with the same velocity in space, like 3 into 10 to the power 10 centimeter per second, as we discussed earlier. All transfer energy from one place to other place in quantum. In free space, they all travel in straight lines, passing through the matter. The intensity of a radiation attenuation because of a two factor get attenuated because of a two factor. One is the energy taken by the medium or material, the absorption. Second is the scattering. So that if any beam incident on any material, there are two things happen. One, a portion of energy is being absorbed and a portion of energy is deflected. The absorbed portion and the deflected portion is called scattering. Scattering is for very important to understand because it is basically involved in the radiation protection measures. Effect of radiation to the material depends upon how much energy the medium has received from the beam. I mean, that effect is directly proportional to the energy which is being received to the material of interest. In free space, all electromagnetic radiation follow the inverse square law. For a point source, radiation intensity at any place varies inversely at the square of the distance from the source to the place at which the intensity is being measured. Means intensity is inversely proportional to 1 by d square. So, since depend upon the distance, so as closer as the source is there with the tumor tissue, this formula inversely square law is strongly applied here. So that is the indication that a brachytherapy, interstitial therapy is entirely more depend upon the inverse square law rather than when the source is from a distance. So in the brachytherapy, this is very much applicable. So now let us see about what is the particulate radiation. One electromagnetic radiation we discussed. The particulate radiation, energy propagated by the particles such as electron, proton, alpha. We have electron treatment as of now. We have a proton treatment as of now. Clinical viable option. An alpha particles is not being used. A neutron and a heavy charge ions called elementary particles. The speed of these particles depend upon their kinetic energy and less than the speed of a light in the vacuum. So these are the particulate radiation. The fundamental concept of radiation physics. The element may be described as a single substance which cannot be made simpler by chemical methods. When the element join another element, or several others result in a compound. So element is basically a unit. So which we make another element, different kind of element, they make a compound. The smallest particle of element is an atom, while the smallest particle of a compound is a molecule. So it is one step ahead. A molecule is one step ahead to the atom. Molecule may be split into the atoms. When it happens, the chemical property of a material will be changed. Like molecules, atom can also be separated into compounds, though the process is much more difficult. The atom having a center is a nucleus, which is having a practically all weight of an atom, because the neutron and proton is, this it's confined in the nucleus, which carry a weight. Electron have a very low weight. Negatively charged particles, outer orbital electrons, they do not carry weight. So that's a very, so atom having a center in a nucleus is practically having the total atomic weight of an atom. A different atoms having a different electron number in their outer circling orbits as different weight and a different positive charge of these atoms. So complete atoms are electrically neutral. Why? Because there is a number of electrons in outer orbit and a number of proton inside the nucleus is equal, and a neutron does not have any charge. So that's why they are electrically balanced. So atomic number is basically the number of electron and the number of proton. And atomic weight is basically, atomic number, if you want to say, either it is number of electron is stable atom, or number of a proton or number of protons is basically atomic number. But when we claim the atomic weight, number of protons in the nucleus and the number of neutrons in the nucleus, that composed of atomic weight. So electrons move around the nucleus in the series of a cell at a varying distance from nucleus. They can never be an electron in between the orbits. So all our electrons are circulating in the orbits. There is never an electron in between the shells. The electron can be accommodated in the orbit closest to the nucleus. The closest is being described as a K. The most inner orbit closest to the nucleus at a rather greatest distance is a L orbit, which can take up of maximum 8 electron. So M can also NO, and this formula is 2n square basically. So that number of electron is increased like as much as the higher the orbit, the number of electron increases in the 2n square formula at T 3250. So electrons are held in the orbits by electrostatic bond, electrostatic attraction, and their negative charge and a positive charge of nucleus. So the number of electrons on the negative charge and the number of protons inside the nucleus is a positive charge. They have a binding force. The force is naturally greatest of electron. Those electrons those are present in the K orbit, the orbit which is closest to the nucleus, because the nucleus has a positive charge and they have a strongly hold the electrons of the K orbit. But the electrons, those who are on the outer and more outer orbits, they progressively get weaker binding force. So removing these electrons from the most outer orbit is better easy than removing the electrons from those who are closer to the nucleus. You see here, for example, electron in a carbon atom, atomic number 6, binding force is 0.28. But the sulfur atom, atomic number is 16. But the K electron binding force increased to 2.5. So as the atomic number increases, the binding force increases. So energy level, you see the copper and then the tungsten, atomic number 29 and tungsten 74. You can see here there's that binding force of a NMLK. So K have a binding energy is 9 keV. Once you go one step outer to the outer orbital electron, they have a binding energy 1.1, and then you see here LMN, that's a binding energy getting decrease and decrease. So number of electron according to 2n square formula, 2 in a K, 8 in the L, 18 in the M, and that's why they change accordingly. So diagram shows the K electron difficult to remove and a tungsten electron at each level much tightly bound to then its counterpart copper, because tungsten has a atomic number. So there are two things. One is the atomic number. The same tungsten K electron binding energy is 69 keV, but the same K electron in the copper is having a binding energy 9. Why? Because the tungsten have a higher atomic number, means a higher proton charge, proton in the nucleus, that is a positive charge. So this is the basic things which we know. So what the ionization excitation? The normal atom is electrically neutral due to net positive and net negative charge. Removal of one of the electron upset this balance, and resulting atom will have an excess of positive charge. It will be another positive ion, When the electron attached to the normal constituent, it creates a negative ion. Process is called ionization. Ionization means if any electron is detached from the atom or any electron attached to the atom, it is the ionization. But excitation, the no electron is removed or attached, but just one electron is sent to the higher energy, higher means sent to the higher orbits, and then same electron returned back with a production of an electrostatic characteristics X-ray. This is basically ionization and philosophy of ionization and excitation. That's where when electron transfer from one orbit to another closer orbit to the nucleus, it must surrender some energy because the outer orbital electron, outer orbital electrons do have a higher energy, and then when it has to adjust themselves to the lower, closer to the nucleus, it has to release some energy, which release in form of X-ray, characteristic X-ray. So you also see here in this figure the binding energy like K, L, M, N. The K electron copper 9 kV, L 1.1 kV. So when electron given 30 kilovolt kilo electron volt energy, and then you see if 30 kilovolt energy is being given, so 9 kV is basically the, if binding energy is 9 kV, so that if you give 30, then 21 kilo electron volt energy of electrostatic X-ray will be produced, or the energy has to be released. So the excitation, ionization that I've already told, rising of electron to another higher level is a process of excitation. No electron, an electron unstable orbit ultimately returns to normal state with the emission of a characteristics radiation, emission of a radiation. So ionization basically gives electromagnetic radiation, and excitation gives basically visible or ultraviolet radiation. It's one of a type of electromagnetic radiation. There are some features of a photon, electromagnetic waves. All the electromagnetic radiation, X-ray or gamma rays, which are of our special interest, traveling with the electric and magnetic field, transfer of energy from one place to another, or a change of energy converted one energy to another form of energy, like a formula of E is equal to mc square. The intensity is the amount of energy passing per unit time per unit area placed at the right angle is basically cause intensity energy per intensity I is equal to E upon A square, means E is equal to arcs of energy passing a square window whose side measure a centimeter. So there are nuclear particles, which is particulate radiation we with a special interest, like alpha particle having a high atomic number, and a particle they have atomic number is more than 82. More commonly decay with the emission of alpha particle, like radium is decay with a radon and helium atom having a 2 proton and a 2 neutron in its nucleus. The property of alpha particles is mass is 4 times that of hydrogen nucleus. Because of large mass, they produce densely ionizing radiation. So the densely ionizing radiation is basically consume its all energy in a very confined area. So make this beam less penetrating. So that is the drawback of this. The very much less penetrating makes this difficult use in the clinical radiation oncology. Now we will talk about the beta particles. They are negatively charged particles emitted from the nucleus. Since electrons are not a part of nucleus, It is believed it is created and ejected from the nucleus in the process of radioactive transformation. Like you see, this cobalt 60 decay with a nickel and a beta particle, and as well as energy, gamma rays. So, if you say the source of gamma rays in what is this? I mean, which are the things which released by the cobalt in clinical oncology? The cobalt machine release to only gamma rays. So what happens to these beta particles? I mean, the beta particles also release. Because of that, there are double shielding of a cobalt source which which stop the beta particle emission from the cobalt source because of a double shielding. So the beta particle have a range of a few centimeters in the medium depending upon the energy. Beta particle are lighter in mass, produce less ionization. A beta particle easily absorbed in the medium is a penetrating, so that its penetrating power depend upon the energy and density of a medium. The another is a positron. It has a unit positive charge, almost no mass. Positron emission is not as common as beta emission. So the K electron capture theory, this which I have already discussed in this process, decay proton change into the neutron after capture of electron from innermost K orbit. Valency of a K orbit is filled by the electron from just outer orbit. This commonly accompanies by the emission of characteristic X-rays. So the gamma rays is never emitted directly. Gamma rays emission is always preceded by some particle emission such as beta particles. I have told you the example of a cobalt. If a nucleus still have energy after emission of a alpha or beta particle, it is said to be in excited state and excess energy released in form of a gamma rays. Gamma rays are like X-ray, highly penetrating. They possess no charge, no mass. They produce indirect ionization. So now that's a very clinical part of electromagnetic radiation, the interaction of radiation with matter. When the radiation beam passes through the medium, because it gets attenuated by the process of scattering and absorption. If a beam is passing, there are two things which need to happen, because energy, you cannot destroy the energy. Either it is being absorbed in the medium or it is being kicked off or scattered from the medium. So both are important. For protection purpose, the scattering is important, and observation for treatment purpose, the absorption is very important. The incident beam attenuation take place by 4 different processes. The absorption and scattering is important in radiotherapy because radiation measurement and radiation protection. What are the points to remember in these? The all effects of radiation, physical, chemical and biological, depend upon the energy absorbed. Energy absorption process can be used to detect and measure the radiation, and the shielding requirements are decided by scattering and absorption process. So the all 4 processes are coherent scattering, photoelectric effect, Compton effect and a pair production. So in coherent scattering, it takes place when the very high atomic material is get interacting with very low energy X-rays and gamma rays. The electron is not basically ejected out, it's only set into oscillation and no energy is transferred. The same wavelength of a photon, and then you see here in this figure the same wavelength of a deflected photon. So it is not important in radiotherapy point of view because no energy is being transferred, only the rays is deflected. The second is photoelectric effect is very important. This process takes place between the incident photon and a bound electron of atom. The entire energy of photon transferred to the electron, thus the electron get ejected out from the atom, ejected electron called photoelectron. So binding energy you see here, B is binding energy. Energy is where h nu energy of incident photon, h nu, and E is the energy of photoelectron. The ejected electron creates a vacancy in the K cell, which is filled by the outer orbital electron with the emission of a characteristic X-ray. You see here the incident photon deflected with a photoelectron, incident photon, photoelectron, and then remove the electron from the innermost orbit, and then the vacancy is filled by the outer orbital electron, and then a characteristic X-ray is produced. You can see here the photoelectron which is removed, and then that's a. What are the features of photoelectric field? Probability of ejected electron is maximum when the photon energy is just higher than the binding energy of electron. Photoelectric effect attenuation coefficient strongly depends upon the atomic number of a material, like inversely, proportional to the Z cube. That is a this way. This is why we use high atomic number material for radiation shielding. When high energy photon falls on the atom ejected in a forward direction, and if a low energy incident photon, the electron ejected in the right angle to the incident beam. The photoelectric effect of a radiation observation is basically effective up to the 60 kV energy level. 60 kV. So this effect dominates. The second is the Compton effect, which is more practical or more viable more of interest in the basically in the radiotherapy, when the incident photon interact with the outermost orbital electron and an atom which have a low binding energy compared to the energy of incident photon energy. That electron is released, that is called free electron. Here only part of energy is transferred to the free electron, and photon is scattered with the energy with a low energy. So energy of electron and the scattered photon depend upon the angle of scattering. If the photon hits directly, the free electron travel forward direction and receiving the maximum energy, and then the scattered photon travels back, this receiving a minimum energy. So maximum energy is transferred. Since the interaction of a free electron is independent of atomic number of a material, the observation of this process is nearly equal for all equal atomic numbers, different type of a material and a medium. So that's Compton effect is very important. Like you see here in this figure, the incident photon hit the bond electron, free electron, the Compton electron released, and this photon deflected with a low energy from the different direction. The pair production, here the incident photon completely absorbed and they converted into a pair of positive and negative electrons. This process takes place in the presence of nuclear field, and a minimum energy for ion pair production required 1.02 MeV. It's also annihilation type of radiation. Minimum energy required for production of ion pair is called threshold energy, and basically pair production is usually happens on the more than 10 MeV energy beam in more than 10 MeV energy beams, high energy linear accelerator. They do have a pair production effect. You see this 1.0 to 0.51 MeV positron, 0.51 MeV electron is used, and this concept is used in the basically in the PET scan when these two different both positron and electron move from the 180 degree. The gamma camera is set along this thing to capture this kind of production of positron and electron and convert the imaging. The silent features of pair production interaction of incident photons take place with the nuclear field of atom. Pair production with an energy of incident photon probability rapidly rise when rapidly with high atomic number, and atomic number is usually square of the atomic number. The pair production dominate with energy more than 10 MeV and above. So basically in a cobalt system your interest is a Compton effect. They are on the medium and less than 10 MeV energy, and the Compton effect is there, and the photoelectric effect is more dominant in the kilo voltage energy, not mega voltage. So you can see here in the summary, like up to 60 kV photoelectric effect dominates. 60 to 90 kilo electron volt energy photoelectric effect and Compton both are there. 200 kilo electron volt to 2 MV Compton effects, 5 to 10 MV pair production and a Compton effect, and more than 10 MV pair production dominates. Thank you very much. Let's sum up with this lecture. Hope you understand little bit of my this lecture. There was not less, what figures and slides were very less, and because it's a more theoretically, but we understanding the line, go through the one line by line, you can understand the concept of electromagnetic radiation. And then second, with the interaction of matter, you clearly understand and thinks of and repeatedly study, so that you are well versed with the all four effects of like coherent scattering, photoelectric effect, pair production, Compton effect, annihilation radiations, so that you are well versed. Thank you very much.